Hang on. Okay, so this is a proof. I've got the proof in inverted commas because the proof isn't really quite comprehensive, but it's not too bad. So what we're going to do is we're going to construct a perpendicular line from vertex B down to the opposite side. Okay, so let's label those sides now. So the side opposite A should be lowercase a, the side opposite C should be lowercase c, and the side opposite B, I've split into two, but the total distance is B. Okay, so what I'm going to do now is I'm going to just use the shorter length here, I'm going to call X. And if the shorter length there is, well, the left-hand length, I shouldn't say shorter. If the left-hand length is X, then the right-hand length is B minus X. Might write that a bit bigger. Okay, good so far? So if the left-hand side is X length, then the right-hand side is B minus X. Okay, so looking at this right-hand triangle, from the right-hand triangle, in the right-hand triangle, we have from Pythagoras' theorem, we have c squared equals the height of that triangle, h, squared, plus the bottom length of that triangle, which is b minus x. So I've got h squared plus b minus x squared. Now, we don't know what h is, and we don't know what x is, so we need to figure out what they are in terms of a, b, c. So in the left-hand triangle, what have we got? We've got h squared is equal to, oh, hang on, I'll do it in two steps. We've got a squared is equal to x squared plus h squared. That's Pythagoras' theorem because they're just right-angled triangles. So h squared is equal to a squared minus x squared. So that means that c squared equals a squared minus x squared plus b minus x all squared. Yeah? So I've just replaced h squared with a squared minus x squared. Now, if I expand that a little bit and simplify it, I get a squared minus x squared plus b squared minus 2bx plus x squared. That's just the expansion of that. Okay, that's a straight perfect square expansion. And can you see that this and this will cancel out? So this minus x squared plus x squared is 0. And so I'm left with a squared plus b squared minus 2bx. So that's all right. Nice and much simpler. And can you start to see that there's a little bit of the cosine rule coming out here? I've got the a squared plus b squared. I've got the 2 and the b, but I've got this x. If I can get rid of the x, then I'm going to have my cosine rule. And if we look at the left-hand triangle again, I can work out an expression for x. So we've also got the cosine of c is equal to adjacent over hypotenuse, x over a, which means that x is equal to a cosine c. And now I'm going to take that and substitute it in for x. So I get a squared plus b squared minus 2b a cos c. and I can rearrange that a little bit. So I get c squared equals a squared plus b squared minus 2ab cos c. Done. So it's quite elegant, isn't it, really? So we do it by splitting up the triangle. What's the time? 9:25. As a bonus extra, let me do a quick proof of the sine rule as well, which is actually easier than this. This is the harder one. So yeah, take time to work on that though, work your way through it, maybe have a look at the video again. Really quick, I know that's probably going to be a bit too fast for the time I've got, but really quick proof of the sine rule. You kind of do it basically the same way. You drop a perpendicular line down from A, like so, and we call that the height of the triangle. Now here we go, nice and simple this one. So we've got, on the left-hand side, so I'm just going to do LHS for left-hand side, we've got the sine of C is equal to opposite over hypotenuse. On the right-hand side, we've got sine of B is equal to opposite H over hypotenuse, which is C. I haven't labelled these in the diagram, but I should do. So I've got A, B, and C. Now, if I rearrange both of these equations, I'll have H is equal to B sine C, and H is equal to C sine B, and we're nearly there. So equating the H, we have B sine C is equal to C sine B. And now if I divide both sides by the sines, I'll get B over sine B is equal to C over sine C. That's one pair. I could choose two other sides and angles to work out that A over sine A equals B over sine B, or A over sine A equals C over sine C, and so on. So basically this is one pair, but because the angles and sides were arbitrary, it works out for all of them. So therefore, A over sine A equals B over sine B equals C over sine C. Okay? And since we don't have a microphone, that's a pen drop. We're done. All right? So again, I'm not saying you'll never be asked in the exam to prove the cosine rule or prove the sine rule, but I genuinely think that if you spend time understanding how it's constructed, not only genuinely think, the research backs this up, you tend to retain the knowledge more and you tend to be able to apply it better to problems because you understand where the rule's coming from. Okay, it is 9:28. You are welcome to leave as soon as you are packed up. I don't know why I left that in the video, but there you go.